Hello.
Yes.
Yeah. Okay, so the last part we are going to do today is the imperfection of solids, imperfection in solids. Imperfection is nothing but defects. Okay, we also call it as defect. So what is defect or what is imperfection? It is the departure of a crystal which is there in ordered arrangement. Means when the arrangement is different, okay. For any crystal, we have seen the various structures, right? NaCl and other crystals, we have seen the structures. So that is the definite arrangement we have, ordered arrangement we have. If there is any departure from that particular arrangement or any change in the arrangement of the crystal, by any means, like suppose if you heat it or suppose if you add an impurities, okay. So any one of these things will change the property of the solids or crystals. So that change in property, that departure from the ordered arrangement is called imperfection or defects in solid, okay. So write down this: imperfection or defect is the imperfection or defect is the departure from perfectly ordered arrangement of constituent particles in the crystal. Of constituent particles in the crystal. Next, write down: perfect or ideal crystal exists only at absolute zero temperature, that is 0 Kelvin. Perfect or ideal crystal exists only at absolute zero temperature or 0 Kelvin. Okay, next line. This imperfection can be intrinsic or extrinsic. Intrinsic or extrinsic. Extrinsic when we add some impurities into this. Intrinsic or extrinsic when you add some impurities, or in presence of impurities will have extrinsic imperfection. Impurities. For example, you see if you have gemstones are the crystal of Al2O3. It is a crystal of Al2O3. And the pure thing is this: the perfect crystal that we have, ideal crystal that we have, it is colorless. Okay, it is colorless in nature. When you add some impurities into this, that is extrinsic imperfection. If you add some impurities, like iron, Fe3 plus iron, if it is present into this, its color is blue. Okay, sapphire blue, exact color if you see. Or if it contains Cr3 plus iron with it, its color is ruby red. This color is because of the change in color is because of the impurities present into this. Okay, so because of impurities, maybe the property of the solid or crystal changes, or it will have a new properties, or the color of the crystal changes. Okay, so all these things, shows the imperfection in solids. Okay, now imperfection we have three types. Mainly we have two types, but total different classification of imperfection. You see, we have three types of imperfection. First one is electronic imperfection. Electronic imperfection, as the name suggests, it is because of the movement of electrons. The second one is atomic imperfection. It is because of the movement of atoms or ions, atomic imperfection or atomic defects. And the third one is line defects, which we also call it as dislocations or dislocation. Okay, line defects is nothing much. We have a solid crystal and the edge of the side changes. There will be some imperfection into that we call it as line defect. Okay, dislocation about a point or along the edge, that is line defects or dislocation defects. Atomic defects or electronic defects, like I said, this is because of the movement of electrons, and this is because of the movement of atoms or ions. Okay, this atomic defects further classified into different categories. Okay, we'll write down everything here, but we'll discuss only few things which are important. Okay, you can go through NCERT, it's given over there. You can just read once, not much important these things are. What are important things? I'll tell you. Atomic defects, we have three types. The first one is stoichiometric defect. The second one is non-stoichiometric. And the third one is we have impurity defects. Give me just 1 second. Okay, so impurity defects, stoichiometric defects, and non-stoichiometric defects. Okay, stoichiometric defects, further it is classified into different categories. Okay, like we have 4 different types of defect into this. Non-stoichiometric defects are also further classified. Okay, so that's why I'm telling you, if you look at all these things, we have a lot of theory to go through it. Okay, so everything is not important, but I would suggest just NCERT you have to read once. I'll just write down all the names here and just tell you the important points, 1-2 important points that we have here. And few things which are important that we'll discuss after this in detail. Okay, stoichiometric defects, we have 4 different types. One is vacancy defect. Vacancy defect. Other one is interstitial defect. Interstitial defect. Next one we have Schottky defect, and one more we have, that is Frenkel defect. Okay, both are very much similar. Means this two belongs to, this two is defined for non-ionic solids. The type of imperfection is almost same, but this two is defined for non-ionic solids, and this two is defined for ionic solids. Okay, type is same, but for ionic, the name is Schottky and Frenkel, and here it is vacancy and interstitial defects. Okay, ionic solids and non-ionic defects, the only difference is here the crystal maintains its neutrality, electrical neutrality, it maintains over here. Okay, so in all these things, till now you can say 90% of the time they have asked question on Frenkel and Schottky. Okay, now coming back to non-stoichiometric defects. Okay, this also we have 2-3 types. Okay, like metal excess defect and metal deficiency defect. 2 types we have here, non-stoichiometric. This is metal excess defect and metal deficiency defect. Metal excess defect and metal deficiency defect. Okay, now you see as the name suggests here, metal excess defect means what? We have more metals present. Metal ions will be more. That is metal excess defect. Okay, so metal ions would be more. So how do we get more number of metal ions? Again, we have 2-3 categories for this. Okay, means we can have metal excess defect in 2 different ways. One is when we remove some anion from the crystal, right? Initially we have electrical neutrality. So metals, positive ions and negative ions are same. So if you remove the anions, we'll have more number of metal ions present. Metal ions means cations we're talking about, right? So in that way, we can achieve this metal excess defect we may have. Another way is what? You add more amount of metal ions onto that. Okay. So the first case by which the metal excess defect possible, that is the anion vacancy by the removal of anions. So in this thing, we have 2 different ways. By anion vacancies, by having anion vacancies. Means what? Anion you are removing from the site. So eventually what is happening? The metal ion is getting more, the number of metal ions is increasing in the crystal. That's why we have metal excess defect. This anion vacancy, we call it as F center. Okay, so we call it as F center. On this also they have asked few questions. Okay, so 1, 2, 3, these 3 points are only important. Okay, but yes, you have to go through once the NCRT, okay, so that you will have the idea of what all things we have. So metal excess defect, one possibility is by removing anions. Another possibility is what? By the presence of extra ions, means extra cations, not ions, extra cations. If you add extra metal ions into that, in that way also, we have metal excess present in the crystal, and hence that also leads to metal excess defect. Okay. Metal deficiency defect is just opposite of that. Remove metal ions from the crystal. Right. So few properties of this will tell you. Impurity defects is what? It is the same thing. Suppose we have group 14 element, you must have done p-type, n-type semiconductor, right? Right. So that is the same thing we have here. Impurity defects is what? Suppose we have any group 14 elements, you add or you mix group 15 elements into group 14. So group 15 plus group 14 gives you what? More number of electrons. So we have n-type semiconductor here. That is impurity defects. Okay. In group 14, you add group 13, that is p-type semiconductor. So this kind of thing we have under impurity defects. So imperfection, we have these 3 types in this. We'll discuss a little bit of electronic defects. We'll discuss Frenkel and Schottky. Okay, important point, difference into these two. And we'll discuss anion vacancy. Okay, a few properties we'll see in metal deficiency defects also. Okay, other things, the deficiency part, the imperfection part, just go through NCERT. That will be more than enough. Okay, so first point you write down, electronic defects. Electronic defects. Like I said, it is due to the irregular arrangement of electron. One second. It is due to irregular arrangement of electrons. So at 0 Kelvin, there's no movement of electrons, and hence we say no electronic movement. I'm just giving you the key points here, that is it. No electronic movement, and hence we do not have any conduction, no conduction. Okay. As temperature increases, transition of electron takes place. Transition of electron takes place. So basically, electrons occupy higher energy state. Takes place, and hence it shows conduction. So when the electron leaves its original site or original position, it creates a hole at its original position, right? So write down, due to the movement of electrons, holes creates, and holes are represented by a small h here. Holes creates at the original position of electron, where the electron was initially present. Original position of electrons. Holes create. Right, next, concentration of electron. The concentration of electron is represented by a small n, and that of hole is represented by a small p. Right, concentration of electron is represented by a small n, and that of holes is represented by a small p. Both electrons and holes, gives rise to electronic imperfection. Gives rise to electronic imperfection. Okay. Next, write down atomic defects or point defects. Okay, atomic defects or point defects are the same thing. This type of defects observed due to movement of constituent particles. Due to movement of constituent particles. So previously it was electrons, here we have particles. So two possibilities we have: when the particles are missing from its original position in the lattice, right? It is missing from the lattice completely. Another one, that it occupies the interstitial sites on the same lattice. Okay, it leaves its original position and occupies the interstitial sites. Okay, both way this kind of defects possible. Okay, so like I said, the point defects are again classified into three categories. That is stoichiometric defects, and then we have non-stoichiometric defects, and then we have impurity defects. So in stoichiometric defects, we have first one we are going to see, that is Schottky defects. Schottky defects. Write down. Write down. It generally observes in AB type crystal. It generally observes in AB type crystal. It generally observes in AB type of crystal, A plus B minus ionic, AB type of crystals. And in this type, equal number of cations and anions are missing from their original or normal lattice sites, original sites. So when they are missing from their original position, it creates holes, right? It is observed in strong ionic compounds like NaCl, KCl, KBr, CSCl, AgBr. AgBr also shows this. Okay. Few properties of this kind of defect you must remember. Like the ions are missing from their original sites. Hence, we can say density of the crystal decreases in this type. Right? Stability also decreases. Lattice energy also decreases. Lattice energy and stability both decreases. Entropy, because the disorderness is increasing. It was ordered arrangement. Defects is all about the disordered arrangement, right? Or the disorderness. So we can say the entropy, because the defect increases. So property-based question they have asked in this. Okay, Schottky defect. Examples and property-based question. Okay. Now the second one is, did you copy this?
sir.
Yeah. Second one is Frenkel defect. Write down. This type of defects observes when the ions, in bracket you write down usually cations, okay, because of the ions usually cations of the lattice occupy the interstitial sites, leaving a corresponding number of normal site vacant, means holes created. Repeating this is, yeah, this kind of defects observes when some of the ions, usually cations, of the lattice occupy interstitial sites, leaving a corresponding number of holes. Next line, it creates vacancy defect. It creates vacancy defect at original site because the position is getting vacant, right? So vacancy defect at original sites and interstitial defects at the new site. New site means where the ions goes. The new site where the ions are present. There we have interstitial defects, and vacant defects at the original sites. Okay, there are a few, we have one or two conditions for this, but obviously we have some exceptions also here. That's why I said you have to, memorize this. For all those crystals whose coordination number is low, can show this kind of defect. Okay, condition. Size difference of anion and cation is more, right? So size of anion is bigger than, or the size of anion should be bigger more than that of cation. So in this case, these two cases, this kind of defect possible. See, alkali metal halides, the size of cation and anion are very much similar, like the difference is not that great. Hence, alkali metal halides does not show this kind of defect. Okay, write down this point. The size difference in alkali metal halides is not high or more . Hence, Frenkel defect is not observed. See, the ions does not leave the site, okay? Means leave the crystal. It is present in the crystal only, but not at its original position. Okay, if you have NCRT, you can open it and you can see the diagram. Okay, or after the class you can see, right? So ions are present in the crystal, but not at its original site. So because of this only, the density change is not there. No change in density. No change in density. Here also, lattice energy and stability decreases, disorderness increases, so entropy also increases. Okay. The molecule which shows this kind of defect is AgCl. AgBr, again I'm writing it down here, it is important. It shows both defects. AgBr, AgI, ZNS, all these shows Frenkel defect. So in AgBr, both Schottky and Frenkel defect observed. Since AgBr is ionic, but again the size difference is also very much. That's why Frenkel it shows. Okay. Yes. Now we'll see one or two things in non-stoichiometric defects. Non-stoichiometric defects. Okay. This kind of defect observes in non-stoichiometric crystals mainly. It is observes in non-stoichiometric crystals. Okay. This also classified into various categories. Like I said, we have metal excess defect. So metal excess defect is possible in two different ways. One is you add the metal ions in the crystal, will have excess of metal, metal excess defect. Other one, remove anion from the crystal. That is anionic vacancy. Write down in this type, metal ions, or in this type, metal ions or cations are in excess This defect may develop in two ways. This defect may develop in two ways. The first one is in two ways. The first one is when excess cation occupy the interstitial position. So number of cations increases, metal excess defect. And the second one is, we call it as anion vacancies. Anion vacancies. Write down in this. Write down when a negative ion is missing from its lattice sites. When a negative ion is missing from its lattice sites, leaving behind a vacancy or hole, which is occupied by the electrons in order to maintain electrical neutrality. The trapped electrons are called F centers. The trapped electron are called F centers. F centers. F centers, which is responsible for imparting color to the crystals. Which is responsible for imparting color to the crystal. This defect is similar to Schottky defect. Right? Similar to the Schottky defect, and it is observed in the crystal which shows Schottky defect. Okay, so this is F center. Just one thing you have to take care of. Write down one note. Greater the number of F center, more will be the intensity of color. Greater the number of F center, more will be the impurities, the intensity of color. Okay, so this is it for imperfection. These two things, they have asked in the exams. Okay, but NCERT, like I said, you must go through. It is completely theoretical. You have to memorize certain things. Okay, and that is it. The first part, you can understand everything logically, all the positions of void and everything. But this thing you have to memorize. Another thing is there is one more thing, that is magnetic property. That is paramagnetic behavior, diamagnetic behavior. We have ferromagnetic substance, antiferromagnetic substance also there. So for that, it's not at all important. But for that, I will share one PDF. Okay. So whenever you get time, you just go through that PDF. It is more than enough given into that. Fine. So this is it for this chapter. Okay. We are going to start next. That is chemical kinetics. Okay. Just 1 minute.